3000, some area will be overlapped. So while mosaicing, that is while joining, we can skip. That is why I told the sun synchronous orbit are placed in such a way that every latitude will have same illumination. So the satellite is now the NOVA is scanning our area. So 3000 kilometers that will cover linear, like that will make. So next pass will come, some of the area will be overlapped. 3000 again. So we can, there is a processing technique that we can merge this, that is mosaicing, that time we can overlap area we can remove. So we can join that. So there won't be much difference because there is sun synchronous means the illumination is almost same. So there is longitudinal difference, time difference. You know that from here, if suppose we are going to UAE, the time will be different. So 10 o'clock we are leaving here, we are reaching after.
So Landsat and WatchSat, what is the time duration for exact repetition of the same swath?
You mean Landsat?
Yeah.
Landsat has got a repetitivity of 22 days.
22 days.
22 days. The swath is very less. You know that 73 kilometers is a swath.
Oh.
If my memory is correct, 73 kilometers is a swath.
73.
73, I think so. So 23 meter resolution. So that can be, what is that? You can rectify when you go for the push probe type of sensor. So that is, I had explained, I had given that is a CCD with lens, this sort of things is a push probe type. So instead of, this is a rotating mirror system is there. So that will it will be rotating, so this will be scanning like this. So the other thing is like this, so that can be rectified. So there are different types of sensing systems. So in general I have told, because time is because in depth I cannot go. So this is, I think this is clear. It is clear now. So now another thing is that can we use all the, we have seen that there are certain regions that is opaque. So I think I have left out some of the terminologies. That is only spatial resolution I had explained. Yeah, that is before this. Yeah, these are all left out. You know that is before that, one more slide is there. So this is the meaning of spatial resolution. So you can visualize this one. That is, this is 0.5 by 0.5 meter resolution. You can clearly you can see the objects. Whereas 1 by 1 little reduced, and 2.5 by 2.5 again, and 5 by 5, that is resolution is 5 meter. So that is again reduced. Then this is 10 meter by. So these objects are not seen in here, and here also it is not visible. So if you are using sort of higher, that is the swath width, that is, you know that the NOVA satellite like that, the swath is 3000 kilometer and resolution is 1.1 kilometer, that is 1000 meter. So you may not be able to see all the objects. So it will, 1 kilometer object, that will be a point. So whereas 1 meter iconos, if you are going, you will get a clear vision of that, those objects. So that is clearly explained. From this you can clearly, you can find out whether what is the spatial resolution, the meaning. So this is this is again, that is iconos, this is Landsat. So this is resolution is 1 meter. So you are getting some objects, you can see some objects. Whereas Landsat, that is 23 meter or something resolution is, you may not be able to see anything. That is the resolution, spatial resolution. Now spectral resolution, that is, you can, there are in the visible itself, we have seen that visible region of the electromagnetic spectrum can be used for remote sensing purpose. So the visible radiation, that is, you know that is the 400 nanometer to 700 nanometer is the region. That is, as far as the wavelength is concerned, that is from 400 nanometer to 700 nanometer is the wavelength region. So visible has got, So we can use this visible as a whole, that is 400 to 700 as a single channel we can make. One band we can make. Instead we can again split into three, that is 400 to 500 one band, 500 to 600 one band, and 600 to 700 another band. So one band, that will, the meaning is that the spectral resolution of that one, it is the visible remote sensing, it is, the spectral resolution is 3, that is, this visible itself is categorized into 3 regions, 3 groups. So the radiation which is coming from the object, that is pertaining to 400 to 500 will only absorbed by the selected band, that is sensor is designed like that, so that the radiation comes from the objects, that particular wavelength only will be sensed. Can I get? We know that near infrared is the, mid infrared is the, then thermal infrared is the, and far infrared. So all together you can that is you can make discrete bands. That is near infrared starts from 0.7. So 0.7 onward, that is 700 nanometer or 0.7 micrometer. So here onwards is the near infrared to 1.25 or something. I am not remembering the correct region. That is 1.25, I think, up to from here to, that is 0.72 or 700 to 1000 something. So like that we can classify one near infrared. Sorry, here it is the near infrared. One region is classified here. So this is from this region to this region. Again it will extend some more. So this region is band 4. So near infrared radiation which is coming from the objects at particular wavelength only will be sensed by the sensor. Similarly, this one also. This is band 1. This is 500 to 600 nanometer or 0.5 to 0.6 micrometer. So radiation which is coming from the ground objects will be sensed according to that range. So this is split into 3, so that you can say that this is up to near, that is visible to near infrared, it is 4 bands or 3 bands. Then you can say that the spectral resolution is 3. So that spectral range is having split into 3, and so that we can identify. Suppose if we are going for data, we should know the spectral range. So for that purpose, this resolution is made. So the number, this is representing the number of bands in which image is taken. That is the meaning of that one. So we can see one band, that is blue band. This is corresponding to blue wavelength region or the visible region. So that is sensed by one. We can keep one image, one datum. So that is blue band. Next is corresponding to green band. So we can use that. So you know that the vegetation that has got a property, that green reflection, that is we are seeing the vegetation, it is green because it is giving green reflection. So we can use this band for this sort of application, that is green vegetation or some sort of things. But we are in NDVI, we are not using that. Another technology we are using. So red is correspond to some sort of objects. Based on that we can estimate that. Are you following? So like that we can categorize. That is the meaning of spectral resolution. Now the radiometric resolution. So it is the capability of the sensor to differentiate spectral reflection. It is coming from different objects. So that is radiometric resolution is that is based on bit information. That is the binary. You know that it is base 2. So 2 raised to n minus 1. That is the bit information. That means, suppose if a sensing system has 8-bit data, that means it will have a levels of 2 raised to 8 minus 1. How much it will come? 2 raised to 8 minus 1, 2 into 2 into like that. 8 times minus 1, it will 255 you will get a value of 255. The meaning is that this can sense, that is the sensor can sense that digital numbers that is in between 0 to 255 different levels. So that sensor can differentiate the radiation in 255 levels. That is the meaning of that one. So if suppose if you are going for the bit data, that is instead of you are going for a 10 bit data. 10 bit data means 2 raised to 10 minus 1. So 1023 is the different levels. When you calculate it, you will get 1023 levels. So when compared to this 8 bit and 10 bit data, 10 bit data will have the capability of giving more information. Are you following? So this is the meaning of that one is this. I'll show the next slide so that you will get better idea.
So far, what is the highest level? 32 bit.
Yeah, 32 bit, and in when we are doing a processing, there is 12 bit data we are using. That is C this modis. So there is 12 bit. So this is something. This is not. This one is an example for 1 bit data, and this is 8 bit data. So you can clearly discriminate. So here you can say that the objects are very clear. It can demarcate the different different gray levels, different levels. The information can see here, whereas here is everything is done. We may not be able to see differentiate the different pixel. What does it contain? So that is the meaning of radiometric resolution. So now next one is the temporal resolution. So temporal resolution, the meaning is that the time to time, that is the meaning is the temporal resolution specify revisiting frequency of a satellite sensor to a specific location. Suppose we are making an observation of our area, say for example in Delhi. So suppose if we want to get a better temporal resolution, then the meaning is that tomorrow also we should get the information. So no satellite, if you go, you can get today and tomorrow also you can get. Not only that, there are 2 satellites, so every day 2 times you can get the information. So then we can say that it is a better temporal resolution is there for that satellite. So you can utilize for global sort of studies. Whereas if you are going for some other satellite,
this same spot located by 2 satellites, huh?
No. This just representation. This is first pass. So it is sweeping this much area. This is the path. So next time it is coming and making this one. Suppose if it is making today and tomorrow it is making again, or this is coming today after 22 days. In the case of, I think in the case of Landsat or IRS also, and some IRS LIS 3 or something. I think LIS 2, isn't it? What is the repeativity? LIS 2 is 16. So we have to wait for today, and after same path for getting that 16 days, we have to wait for 16 days. So that clearly defined the temporal resolution. So temporal resolution is 16 days means, as far as you are the application scientist, so for the application purpose you have to select the data. You have to choose the satellite sensor. So you can design, you can go for the temporal resolution of the satellite and you can choose according to your application purpose.
Right.
So if you need a data within every day, you have to go for NOAA. Instead, you may not be able to. If suppose if you are taking another vegetation, also will behave like this. Individual, this one will be there. That we have to. Again, we have to. But in general, one object will have the same unique property, unique sort of property. That is it behavior to different wavelength region. It is like this. So this is the signature. So by just seeing this one, so you can, instead of going to satellite, a sensor radiometer you can use. You can from here itself radiation which is coming from the objects can be sensed, and you can make a graph. Then it will be like this. So this is characteristics for the vegetation, that particular object, whereas water is having another sort of reflective characteristics. So this helps in identifying the objects. So the identification of the objects and the magnitude, that is, you can see here, this is 66% moisture content is giving this, and somewhere around 55 or something, 54 to 66% moisture content is showing this one. But pattern is same. Only change will be there in this signature. That is the only change. And this is having another. So like that. So the pattern is same. So this will help in identifying the feature. So spectral signature, that will help in identification of the objects.
This vegetation, we have different types of vegetation. Coconut,
Yeah, that we can. So this. This I have showed, I think. This I have showed. This also I have showed. So now we have reached up to here. That is the. This is the black body radiation characteristics. This is very important in remote sensing. That is, we have to study about the black body so that we will get an idea about the sun's radiation characteristics, and also from terrestrial radiation, how it responds, that is the Earth's surface, how it responds to the radiation that is coming from the sun. So that is, you know that is sun's energy, that is sun temperature is equivalent to 6000 K. That behaves like this. This is the spectral radiance or emittance from the, that is the radiant energy. So we wanted to calculate how much energy is contained in this spectrum. So all the energy we are getting it from the sun. So this sun's energy is concerned, this has got a peak energy, that is from point, this is in micrometer, earlier I had explained in nanometer, so only thing is that 500 instead of 0.4. So this is because for the explanation purpose I took this graph from some other this one, so this is not unique. So this is same, 500 nanometer and 0.5. So this has got, that is the visible range, that is 0.42, this is 0.42, 0.7 has got maximum energy. So that is, as far as the sun's radiation is concerned, maximum energy is concentrated in the visible. So that energy is one of the important aspects. We have to identify the object. So the energy content is very important. So visible has got maximum energy. So visible radiation, which we can use for better identification purpose, because it has got maximum energy content. Whereas this terrestrial radiation, which is correspond to 300 K, that is radiation going back from the Earth's surface, that is equivalent to 300 K. That is, I think it is 27 degrees, isn't it? Around the terrestrial radiation. So the terrestrial radiation peak, if you take, that is corresponds to the peak is, here is peak is 0.52 or something. The peak single point, if you take it, is 0.52. Whereas here it is 0.96 is the peak. So terrestrial radiation, there is radiation going back from the Earth's surface, is confined to this region. So infrared radiation, this is infrared radiation that is going from long wave ranges. That is radiation going from the Earth's surface in long waves are referred as, the wavelength is long compared to this short. So long waves are concerned, the energy maximum is 9.6 micrometer. Or this broad spectrum, that is 9 to 13 or 14 if you take, this contains maximum energy. So most of the satellite sensors which are sensing the thermal properties of the Earth, that is, you know that the sea surface temperature, estimation, the bands are designed to this one. We have seen the graph there. This range is, there is a window there is an atmospheric window, this radiation will go through that atmospheric window, and also energy content is more. So most of the satellites you can see 10.5 to 12.5 is the microwave region for measurement of SST, sea surface temperature, or temperature measurement. So that is because the energy content is maximum here, so we are utilizing this one. For visible, we are taking from 0.4 to 0.6, sorry, 0.7 up to near infrared. Maximum energy is there. Peaking around 0.52, here peaking around 9.6. So these bands are exclusively used for exploitation of this sort of parameters. That is, say for example, the sort of things, that is the chlorophyll estimation, we are using this visible. Suspended sediments, we are using this one, the CDOM, that is dissolved organic matter, the CDO, the C for what? Colored dissolved organic matter. So for that, it has got some yellow color has got some correlation. So we are using that, and also the blue absorption is there 0.43 micrometer or 430 nanometer. There is an absorption. So and also the yellow has got reflected. So these principles are used for estimation, and chlorophyll I have told the principle absorption and scattering. So here this is the principle, that is this is required for this black body.